You in the Jamboard, right? So just click on this next button or click on the frame here to move, navigate between the pages. And just answer it verbally. So how do you answer question 1? Just talk to me, tell me, not no need for typing. You just need to take note in your notebook writing, okay? If you see that it is important, it is surprisingly different from your initial thought.
So, Joe pulls with the
What
force.
the force of Helen exert on the ring?
It's 40 newtons. 40 newtons.
It's so difficult to hear. There's a problem with the headphone.
No, I disconnected my headphones, so I'm
Yeah,
hearing clearly.
with the laptop, it's a very low, sound level. It's difficult for me to hear.
So I just write my answer there. So
40 newtons.
yes.
Uh, the answer is not 40 newton. Wait. In one direction, then you with the force of Joe pull. Okay, let me draw that. Yeah, probably you're right. For example, we say a metal ring. Joe pull 100 newtons here to the left. Daniel 140 newton in the opposite direction, a little bit longer. Okay, yeah. So Helen has to exert a force in the same direction with the 100 newton force. Okay, and it's 40 newton. You're right. What for Helen is to put it in the same direction as Joe. Okay, so this is the direction of Joe, and Helen also in the same direction, huh? And the other person, Daniel. Yeah, you're right. Question 2. A boy drags a suitcase along the ground with a force of 100 newton. If the frictional force opposing the motion of the suitcase is 50 newtons, what is the resultant forward force on the suitcase?
Um, it's 15 newtons.
Yeah, yeah, exactly. Pretty simple, huh?
Yes.
Um, 100 newton pulling force, 50 newton friction. So the forward force is the difference between 100 and 50. We see the forward force, we can call it the net force. Okay, net meaning the sum, the total.
Okay.
A picture is supported by two vertical strings. If the weight of the picture is 50 newtons, what is the force exerted by each string?
25 newtons.
Yeah. Divide 50, the total weight, the weight of
Right.
the the weight of the picture is 50 newtons. So each string must exert a force of half of that, meaning 25 and 25. So that the sum of the three forces is 0.
Yes.
Question 4. Using a scale of 1 centimeter to represent 10 newtons, find the size and direction the resultant forces of 30 newton and 40 newtons acting at right angle to each other. For this question, I'd like you to draw on your notebook and take a picture and send me on Zello.
Okay. Sure.
Mm. Then we will look at some past paper question to see if there's some challenging question that was doing and move on to the next topic. You said matter, huh? And then pressure. So what is the strange thing that you struggle with the topic matter?
It's actually about like the formula and uh the constant. something. Yeah, it's a bit hard for me. So
What formula?
the formula to calculate the load of a spring.
Calculate what? It's just difficult with your microphone.
The formula to calculate the load of a spring.
The lower spring. It's like Hooke's law. It's related to the extension of a spring, right?
And the constant of the spring. Yeah, something like that.
Okay, that's Hooke's law. So we will learn Hooke's law later in like 10 minutes.
I started my drawing.
Okay, I got it. We copy that. Yes, that's good drawing. Well done. There's a problem with my keyboard. Please wait 1 minute. Let me fix the keyboard. Okay. This is your drawing. It takes some time because the photo that we take with the phone is like high quality and high megabyte, huh? Dung lượng. Okay, that's good drawing. Like 3 centimeter for 30 newtons, huh? 44 centimeter for 40 newtons, and then we draw the diagonal of this rectangle. Yeah, and if you already studied trigonometry in a right triangle, the hypotenuse, Pythagorean theorem, remember?
Yes.
The hypotenuse of the triangle, let's say the total force, F net, according to Pythagorean theorem, is a square root of 30 square. Newtons square plus 40 Newtons square, huh? And it will be 50 Newtons. Or you just need to use a ruler. For many cases, for some exercises, you can use a ruler to measure the length of the arrow, the vector, and therefore with the scale that you draw the diagrams, you can calculate the force without using much of mathematics. Okay.
Yes.
Let's practice a little bit with the question of forces before moving on to Hooke's law, like 1/3 of this document. This is the link of a website containing all the past paper questions for all the topics. We see about the first topic, general physics. Okay, we have 5 topics and the practical experimental part. Okay, and we are on the first topic, general physics. The first document of the past paper here. Okay, question paper masking. And I've just downloaded that document and put on a drive. I send you the link to that drive later. Okay. So I just want to send you this link for now to save in a folder that you can open easily like later.
Okay.
And we're doing the question on here, this link. So for easy question, you just answer me verbally, okay, by talking. And for difficult question, if you don't know how to do it, ask me. State the factors which completely describe a vector quantity. I'm so sorry. Please forgive me for 2 minutes. Okay, can you answer question 1A? The factor which completely describe a vector quantity. Actually, there are. Hello?
Hi, I'm here.
There are 3 factors, not just one. Can you answer that?
3. The length.
That is actually magnitude.
The magnitude.
Magnitude. Okay. And
The direction.
direction. And
The point of action.
yeah, acting point. Point of action. Okay. Question B. An aeroplane flying towards the east in still air at 92 meters per second. A wind starts to blow at 24 meters per second toward the north. Draw a vector diagram to feel the resultant velocity of the aeroplane. Resultant velocity. So this is the addition of the 2 velocities. This is the main velocity of the airplane, east, okay? And the velocity of the wind is called the drag velocity. Drag velocity. So you need to draw 2 arrows perpendicular to each other and then add them similarly like what you did with the 30 and 40 newtons, okay? But
Yes.
with the correct scale, 1 centimeter for 10 meters per second, But drawing 92 meters per second, like 9 centimeter, that is too long, huh? So I recommend you to use like 0.5 centimeter for 10 meters per second. But in doing the test, this is a real past paper test, okay? So anyway, so you should use the given scale, 1 centimeter for 10 meters per second, and please do that in your notebook, on your notebook.
Okay, sure. Can I just use a box to represent the airplane?
You just need to use one point. You will learn later the thing called free body diagram. You don't need to draw an airplane, just one single point, okay?
So I just need to...
my keyboard again. You just need one point for the airplane, 92 meters per second to the east.
Okay.
92, and the north wind velocity. Check if I can copy the link. Is this somewhere? Yeah. Okay, good. Wait, the force of the wind is to the north, not to the west.
Oh, to the north.
Uh-huh.
Sorry, I just...
To the north, so the two vectors are perpendicular to each other.
Okay, sorry, so I'll draw it again. I didn't pay attention to the
Direction.
Yeah.
Direction is very important because that is the main property of a vector. The scientists invented the concept, the definition of vector, because they want to know the direction. They want to describe the direction, like where the object heading to, or which direction a force acts and pull the object to accelerate to. I'm wondering if you can copy the the photo and paste here directly on this PDF. No, yeah, so I have to like text view. Add photo PDF extension.
Yeah, I just sent you.
Okay, 24 meters per second. Okay, that's good. Correct. Well done. So, did you use the Pythagorean theorem to calculate the resultant velocity, or just measure the length?
I did both, like for the
Okay.
the mix
Okay.
upgrade.
Okay. Looking for picture from this side. There's like no way for me to add a picture on this, but anyway, you drew it in the notebook. That is the main point. To save the time, so that we can study the next topic about spring and Hooke's law. We come back to the topic of force later. Okay, this is we're learning Hooke's law now. In the beginning. Okay. We have a spring, and when we hang an object on a spring, it will extend. Obviously, of course. Let me find a experiment to explain how we discover the relationship between the weight of a hang object with the elasticity, the stiffness of a spring. Okay, Hooke's law experiment. So we hang a spring on a stand like this and put a ruler behind vertically behind the spring. Okay, so that we can measure the length of the spring. Make sure that we put our eye at right angle at the same level with the reading at the end of the spring to read the value, the length of the spring correctly. Okay, then we will hang an object to the spring. Firstly, we measure the initial length of the spring without hanging any object, the natural length. Okay, and then hang an object with known mass, for example, 100 gram to the spring, and measure its new length. Okay, let's call it L1, and then subtracting L1 from the natural length L0, we get the extension of the spring. Okay, and then replacing, for example, for the force of 1 Newton, meaning it is equivalent with the mass of the object about 100 gram. Okay, because 100 gram multiplied with 10, actually the right value is not 10 but 9.8. When an object is 100 gram, which means 0.1 kilogram. Okay, multiplying it with 9.8, the weight is 0.98 newtons, approximately 1 newton. Okay, and for IGCSE level, most of the time the value 9.8 is rounded, taken to be 10. Okay, so for the first object, the weight of the object is 1 newton, and the pull, the force of its object pull on the spring will be the same, 1 newton. Okay, the weight 1 newton, the pull 1 newton, and the spring will exert back a force that is called elastic force. The elastic force of the spring is equal to the force that stretch the spring. Cái lực đàn hồi của cái lò xo thì nó bằng với cái lực làm cho nó bị giãn ra ha, cái lực kéo cho nó giãn ra, nhưng mà opposite direction. But the elastic force of the spring is of course opposite direction to the pulling force. Okay, and in this experiment, the extension is 3.5 millimeter. Okay, this is millimeter or centimeter, multiplying with 100. That is 3.5 centimeters. 3.5 centimeter. Next, we add another object onto it here, above the first object. For example, adding the same weight. Now the force is 2 Newton. The weight is 2 Newton. The extension is 8 centimeters, and so on. We have a table, the data table like this. Okay, and then we represent the table, the data by a graph like this. Let me draw it on the whiteboard. Where is it? Oh, I accidentally closed that. No. Let me open that whiteboard again. Probably here. It's like, okay. So next, we will represent this data table on a graph. Right.
Okay.
This is the data table. The vertical axis is the force, which is elastic force. As I said, the elastic force is equal to the weight of the object hanging to it, but opposite direction. Okay, now this is the extension. Let's call x. Sometimes it is denoted by delta x, but just for simple, just x. Okay, this elastic force, and let me write down there. The elastic force equal to the weight, hang weight, but opposite direction. So these are the weights of the hang objects, but also equal to the elastic force. Okay, and then we represent those data on this graph, and we have the points, data point like this, and a best fit line will go through the error bars. I will talk about the error bar next time. Okay, like we determine the uncertainty, the error bar for each value of the extension, and the not as beautiful as this. In reality, the point will be on the two sides of this best fit line. Okay, have you heard that word? Best fit line.
No, not no.
Okay. I'll explain that later. Or we can put this number onto a software to plot the graph. For example, I forgot the decimal. I don't actually remember how to do decimal. Normally, you Excel, online Excel, or just Google Sheet, huh? But in your curriculum, of course, you have to do it manually by hand, not by a software. But I'm just saving time by using the software. So if we work, go to sheet, put the data onto a sheet. Okay, let me change the account. No, this is not my account. Okay, 1, 2, 3, 4, 5. The force F, 1 Newton, 2 Newton, 3, 4, and 5. The extension X, 3.5 centimeter, but let's just write in meter. Okay, 0.5,
Okay.
0.08, 0.08, 1.2127, 0.127, 173, and 0.219. Okay, now let's plot the graph. Insert chart and choose the scatter. Okay, already scatter here, but it is x with f, so I need to change the position of the column. Okay, we'll move the x to the left. Insert the chart again. So here, the vertical exit is the force. It is really written like vertically like this, huh? And horizontal exit is x. The horizontal exit, horizontal variable, the quantity on the horizontal axis is called the independent variable. Okay, let me type here. You should write this thing into your notebook. Independent variable, and the variable on the vertical exit, the quantity on the vertical exit is the dependent variable. Okay.
Can you say again? Can you talk again about the dependent variable and the independent?
Okay, it is called independent variable because we control it at will. What we want to control the extension of the spring by changing the hang weight onto the spring. Okay, and we want to investigate how the elastic force depend on this thing, the extension. Elastic force is the result, and this is the thing we control, and therefore the elastic force is called the dependent variable. Okay.
Okay.
Hooke's law procedure. I explained that by speaking, but I just want to find a website that summarize the procedure, like say my exam. No, they didn't summarize the procedure. Well, probably we can do that in the practical part activity, okay, later. So again, the variable on the vertical axis, which is the elastic force, depends on the extension that we control, okay? So the force is a dependent variable. It is on the vertical axis. And the extension we control is the independent variable, okay? And this is the scatter graph using Excel Google Sheet, and I can manually insert a best fit line. Actually, to draw the best fit line, we have to know the errors, the uncertainty of this experiment, which is not represented in this video. Okay, here. So this person also draw the line, the poise there, without knowing the uncertainty. Explain the thing uncertainty next time. And uncertainty is basically for higher level, high school, not for IGCSE. Okay, so the data in the exercise usually perfect, meaning they lies almost on the same line. I'm looking for the line image. No, drawing. No. I want to insert a line. Where is it? Anyway, there's a function on this Google Sheet. meaning I'm looking for the trend line. Customize series error bars. Okay, trend line. I will hit on this trend line. Okay, and the software will draw a line that is closest to the given data. Okay, describing how the data changes over time for the whole series of the data. Okay, and this trend line drawn by the software is extremely close to the best fit line. Best fit line. For the experiment part, there is always some uncertainty, some error when we do the experiment. For example, for this experiment of the Hooke's law, when we read the value of the extension by our eyes, we can put our head a little bit above the end of the spring here. We can read 32.5 or 32.6 or 32.4. Okay, that is the error of reading. One of the many reasons of the error. Okay, you got the idea?
Yes.
When you measure the weight of this object, it depends on how good our weight scale is. It is expensive and very accurate scale, or a normal and not very accurate scale. So the force, the weight of this thing can be can be uncertain by about 1 or 2%. Okay, for example, it's not perfectly exactly 100 gram, but could be 98 gram or 102 grams. Okay, and so for experiment, we always have the error bars. Error bars. For example, the error bars, the vertical error bars here means the uncertainty of the quantity A. In this case, this experiment, Hooke's law, is the elastic force. Okay, and sometimes we also have the horizontal error bars, which is the extension of the spring. It can be the length of the horizontal error bar could be 2 millimeter. Okay, because we read the value could possibly wrong by 1 millimeter. Okay, so for higher level in high school, grade 11 and 12, you will also need to draw the error bars, horizontal error bar and vertical error bars, and then the best fit line that passes through all of these error bars. For example, here, the two red lines are the worst fit line. The worst fit line. Okay, the two worst fit line. The two red lines. Okay, the worst fit line go through the highest point here and the lowest point here at the bottom. Okay, another worst fit line go through the lowest point on the top and the highest point at the bottom. Okay. Cái đường worst fit line này nó đi qua cái điểm cao nhất ở phía trên này và điểm thấp nhất ở phía dưới này ha. Và cái đường worst fit line thứ hai nó đi qua điểm thấp nhất ở phía dưới này và cao nhất phía trên này. The best fit line does not is like lies between these two worst fit line. It will go so that all the data points like resize, distribute evenly on the two sides. We have like 8 data, 4 data will be on the above the best fit line, and 4 data will be below the best fit line. Some data point could be on the best fit line. Okay. Like this red line. But again, this is for high school, not your current level. And your level now, it's just a beautiful line, perfectly ideally like this. So that is the graph of the force, elastic force versus the extension. And that graph will go almost through the origin. So this is a linear relationship. Okay, linear relationship, and it is represented by this straight line, linear relationship, linear function, and Hooke's law discovered this relationship F equal K times X. X is the extension. F is the elastic force. Okay, to another color. Elastic force. And this coefficient K, coefficient K here is called spring constant. Spring constant, or sometimes called elasticity of this spring. Okay, the spring constant means when the extension is 1 meter, the force is, for example, 100 Newton. The spring constant means how much elastic force the spring generates when it is extended by 1 meter. Okay, let me type it down. The spring constant represents how stiff a spring is given it is equal to the elastic force that the spring causes when it is stretched or compressed by 1 meter. Okay, this is the definition of the spring constant. You got that?
Yes.
Nó là cái độ lớn của cái elastic force. Ví dụ 100 Newton khi mà cái lò xo đó nó bị kéo giãn ra 1 mét hoặc là bị nén lại 1 mét. And its unit is Newton per meter, 100 Newton per meter. Okay. Newton per meter, K equal that. Nghĩa là khi mà cái lò xo đấy bị giãn ra 1 meter thì nó tạo ra một cái elastic force là 100 Newton ha. And this is a medium spring, not very hard, because for some strong spring, elasticity or spring constant elasticity. Actually, because elasticity also means another thing in another topic, so we should avoid using the word elasticity, but rather spring constant. Spring constant, strongest spring. Maximum spring constant, okay, 10 to 6 newtons. About that.
Okay.
Strongest spring. Let's see where it is in reality. For example, below some train spring, train wheel, damping system of a train. Yeah. Okay.
Yes.
Or even in some kind of bridges. Yeah. So those springs can be extremely strong. Spring constant. One more thing, this law is not always correct. It has some limit, the limit of Hooke's law, and it's called elasticity limit. Elasticity limit, or another name, linear relationship. Okay, Hooke's law limit. You know, for some spring, when you extend it too much, it cannot restore the original length, original shape and form, or the elasticity of the spring will be changed. It is no longer a constant. It is only a constant when the extension of the spring is still small. Okay. For example, an object like this. This could be a spring or a metal bar that is a stretch. Initially, when the extension is small, the spring constant is constant, and it is described by this linear relationship f equal kx. If the extension is too much, the property of that object change. It is no longer a linear relationship. Huh? It can be a curve like this. It can be broken, okay, and cannot restore the original form, okay. String hardening, neckling to curve. You don't need to care about those things. Just remember that the Hooke's law only valid for small extension, okay, only valid for small extension within
If
the
the extension is too big, it will not get back to the form, right?
Can you say again?
It will. If the extension is too big, so the spring will not get back to the form. It
Yeah,
will go back
exactly. Yes,
that.
it will not get back to the original form and length. We see that normally when we straight the spring in a pen, huh? Straight it too much, you cannot restore to the
Okay.
original length. Uh, there are some other types of material, ductile material and other things, but we leave that for another lesson later. Okay, that's Hooke's law. Let's find some question about Hooke's law. Hooke's law, yeah. Question paper. Let me also download that and put in the folder so that we can dry on it. Save as. Yeah, Hooke's law. Put it here. Okay. Click on allow access. Oh, just let me remove that for now. For the file, Hooke's law. Yeah. An experiment is carried out to measure the extension of rubber band for different loads. The results shown below. Which figure is missing from the table?
Load and then extension. Sure. Let me calculate it.
So we're given the length and the extension. That's a linear relationship. Also the load, so we can calculate the spring constant. Or we can put the values on a Excel Google sheet and draw a line.
Extension.
0, 1, 2, 3. 1, 2, 3. I will put extension is the later length. Subtract the initial length, the natural length. The natural length is 15.2.
Load is 0, and the length, the original length is 15.
15.2. Because a 15.2 original length is 16.2. And let me make another column for the, okay, the extension x is here, which is this value minus 15.2. This value is missing. The other value is 18.6. And the length given in centimeters. Centimeters. Extension. Oh. So the extension down here is calculated by subtracting 16.2 with 15.2 by 15.2. So we're given the extension here, so you don't need to do the division, just add it. Add the extension to 2.1 with the length 15.2. Okay.
Okay.
Ở đây mình có extension 1 này, nó là chính là 16.2 trừ 15.2 ha. Cho nên là
Vâng.
extension 2.1 này thì mình lấy 15.2 cộng thêm 2.1 này là mình sẽ có extension chỗ này thôi. So that extension is 17.3. Answer B. Okay.
Có nghĩa là 12 nhân 2.1.
No. This is extension, meaning the difference between the later length and the natural length. This 16.2 is the natural length without any extension, natural length. See the extension when we hang an object onto it. So the extension is simply that extended length, subtract the natural length. So this value here is 15.2 plus 2.1. 15.2 plus 2.1, which means 17.3. Okay, simply that. We don't need to use a division finding the spring constant. This is just the beginning. beginning. For object X, are each acted on by only two forces as shown. Which object is in equilibrium?
Object B.
Why?
Because the two lines, the two vectors are.
Yeah, they are on the same line, meaning they can cancel out perfectly, cancel out totally. So that is answer B. In this case, 4 Newton upward and 4 Newton downward can also cancel each other out, but each force will generate a torque, a moment, because the two forces are not on the same line. They will generate a torque compared to the center of gravity here. Okay, it will generate a torque, and therefore which object will rotate clockwise direction. Okay. Extension. Load graph spring is shown. The unstretched length of the spring is 17 centimeter, meaning this is the natural length. When an object is hung from the spring, the length is 19.2. What is the weight of the object? 19.2. Okay, I'll let you do that.
I think it's a bit hard to do.
No, it's not hard at all. We say the
no, it's like a bit hard on me to do the because it's on the screen.
Okay, on a string. Do you have a printer at home?
It's the 3 newtons. I have a printer, but I haven't paired it, so it's it will took some time.
Tức là ở nhà mình có máy in đúng không?
Có, nhưng mà ý là kiểu vừa mới lấy về kiểu
okay.
Nên là chưa dùng.
You know, are you using a big monitor or a small screen on a laptop?
A big monitor.
That's good. Yeah. So you can see
I calculated. It's 3 newtons.
3 newtons. Okay, let me check that. The length of the spring is 19.2, which means the extension is 2.2. 19.2 minus 17, the extension X is 2.2, which is here, okay, 2.2. And we draw the line, the dashed line to this, okay, this is the intercept of that dashed line, and this is the reading on the horizontal axis, which is 3 newtons. That is the correct answer. Well done. Okay, that is the method to do this. Next time we will do the type of question that require we write the solution, the explanation, not just circling the option. Okay. The two middle blocks B and Q have identical dimensions. They hang on identical spring balances.
What can be deduced about P and Q?
Identical spring balances. What can be deduced about P and Q?
They have different weights.
Yeah, exactly. Yeah, well done. Different way, and what can we say about their volume? They drawn like the same volume, huh?
So they could be the same volume, but have
Same volume,
weights.
but different weight. Definitely different weight. Answer D.
Yes.
They didn't mention about volume, but we just see the drawing that the same area, same dimensions,
Wait. Different mass. Yeah.
different masses. Yes, different masses. P and Q, meaning different weights.
Okay.
Equal volume, equal weight, wrong. Equal weight here is wrong. Equal mass here, wrong. Different volume, wrong. Okay.
Okay.
So that is answer D. The student adds weight to elastic cord. He measured the length of cord for each weight. Then he plots a graph from the result as shown. What has he plotted on the vertical axis?
Adds weight to elastic cord, measure the
Weight.
length.
Okay. So we see that this is a straight line, a linear relationship. And from Hooke's law, we know that the elastic force is proportional with the extension, but this is the weight which is equal to the elastic force.
Yes.
So the weight is represented on the horizontal axis. So we have to consider each of the quantity measure length. The measure length proportional to the weight. Weight equal elastic force. And this elastic force, according to Hooke's law here, is the difference between the measured length and the natural length. L0 is the natural length and stretch length. Okay, so according to this relationship, we can change this as the following. Change this equation, dividing k on both sides. Okay, f over k equal L minus L0, right?
Okay.
And then represent L as f over k minus plus L0. Okay.
Okay. F over k is x is the extension.
And the graph passes through the origin O. Origin. Original length, no. Measure length, no. Measure length is L here. And this is the y-intercept, meaning it should start from like here, not at origin. So this is not the measure length.
It's not the origin.
Original length also.
It's the measured length.
The difference.
Yeah.
The difference here, proportional to
No, I don't think
yeah, exactly. That is the difference.
Yeah.
Right. You see, this can be like the y on the function, in the function y equal ax, where a here is actually 1 over k and x is the f, the force. Okay.
Okay.
So the difference between the two lengths, meaning the extension, is the vertical, the extension L over L0 here, which is x, the extension. Yeah, that's the way to answer this. And it's kind of interesting, huh? It takes some time. Okay. So that is it for today's lesson. I already sent to you with the link of the document I will later send you the link to this online drive where I save all the notes, recent note, okay, and the board here, export it to PDF. But I recommend you to write on your notebook because that is better for focusing.
Okay.
Course and books law. See you later next Monday, 8 p.m.
Yeah, sure.
Yeah. Bye.
Yeah. Bye.